the primary reference that I'm using for this talk is cylindric set algebras and related structures. And we acronymize this for the sake of referencing. So every time you see a footnote, I'm using that book. Um, and also any definition that's referenced in the slide is also from that book. I've also used Hale-Mosch's algebraic logic, Cohen's set theory and continuum hypothesis, and Klein's meta-mathematics as some essential background. The authors of my primary reference do go through metalogical and algebraic background, and I have not hesitated in using that for my talk. I will do a bit of hand waving, but this talk is meant as a motivation for cylindric algebras as methodology, and I hope to convince you of that. So we jump into some of the background. So we define a logic in the most general sense. So we've got a universal set, a set of variables that can contain elements from that set, a set of relations, and a set of operations. We've also denoted some notation here for what a term is, and it's basically the simplest elements and the elements that we can construct from those simplest elements. We've also established some basic model theoretic notation that we can use, so structures that can model certain behavior in a formula or a set of sentences. Um, so we define what a consequence is in terms of a model. So that is, if the model of a set of sentences, that is the consequence, is the subset of the model of the reference formula. We also have something called the consequence operator, which allows us some intuitive space to later understand Robbin's problem. So someone else before me did go through completeness and consistency, but I will define what a theory is. So a theory is a set of sentences that are true when interpreted in a particular model. And the previous presentation also talked about decidability. So a surrogate of that I've here used as axiomatizability, where I've used the consequence operator. So we're jumping in to some of the algebraic background now. So we've moved down in order of particularity. So a relational structure is just a universal set, a set of relations and a set of operations. A specific case of that is an algebra, which is just a universal set and a set of operations of arbitrary rank, which is the most general form of definition that we can make compared to what we may have seen before in terms of an algebra, say in terms of a vector space or a ring or a module. And we just define a distributive lattice. So this is just a lattice where three arbitrary elements follow the given equation. So that's useful when we define a Boolean algebra. So that is a distributive lattice that has distinguished elements 0 and 1, and that satisfies the two equations given down below, like 1 and 2. So notice here that we also have the product operation. Paul Hale-Mosch also simplifies this further to the following. His statement is a Boolean algebra is a ring whose every element is idempotent. The sum and product here correspond to or and respectively. And the tuple of the arity of each operation in order is called the similarity type of an algebra. And algebras which share the same similarity type also share some structure which can act as models for each other. So we now define what a cylindric algebra is. So that's some structure which has two additional distinguished elements, one of which is unary, called the cylindrification operation, which corresponds to the existential quantification in logic. And the other is also a binary operation and is called the diagonalization operation, which indicates equality between axes of variables. So so again, C sub kappa corresponds to the existential quantification over a variable, and variables here are represented as axes. So what an axis means in this case is it can hold a certain array of possible values. And we don't need to remember all the postulates that we've defined here, but if you notice C5, that's just reflexivity. C6 corresponds to transitivity, and C7 is the property of non-contradiction in a logical system. Um, so stripping away the added distinguished elements, one may obtain again the original Boolean algebra. So the Boolean algebra is of course like a part of the cylindric set algebra, and that's technically called an algebraic reduct of the cylindric algebra. We can also generalize the operations of plus and product and replace them with joins and meets from lattice theory. And if we are allowed that previous generalization, we are also allowed this to set as the set of operations of union and intersection. So we're replacing joins and meets with unions and intersections. The set theoretic versions of cylindrification and diagonalization are represented here. So this allows us some glimpse into the intuition behind this construction. So C is trying to compare all tuples of a certain cardinality and compare the particular axis to the one in reference. And D follows in terms of equality. So it's a similar kind of intuition. So the we've also defined a base here. So that's just the free variations of all possible values of all variables. So we have a closed form formal definition for a full cylindric set algebra in the sense that its universal set precisely accommodates a base set and nothing more. We also have the standard definition for a congruence relation. And the set of congruence relations are especially important because it signifies equality of truth value. So we have again, so the intuition for quotient algebras that we have in abstract algebra, we port that into here. So it basically leads us into sets of equivalence classes, and the simplest version of that maps more complicated sentences to simpler ones that are known to be either true or false. And Okay, we shift gears now a little bit. So the most general form of an algebra that one can conjure is the free algebra, and its set uses a two-dimensional Cartesian identity operation because we can ensure that only that an element equals itself. Very simply, it allows all possible permutations of allowed conjugations between elements. So relating the same algebra to logic now. So if you have one of the formulas of a language, this results in an object called what we call a free algebra of formulas. So there is some rich theory here in relation to ultra filters, which try to seek out large subsets, and I can point you to this Polish logician named Losch who did some work on this. Um, so the set of axes that a variable depends on is the dimension set. The cylindrification remains invariant, which means because each variable fits perfectly and therefore constitutes the axis set in an abstract sense. Um, yeah, so local finiteness here is, I've just put it here for the sake of completeness, but each variable of the set has a finite dimension set. So I can motivate its importance by saying that studying its ultra filters and using the completeness theorem allows us some insight into certain properties that make it nice to work with in the undefined way that mathematicians call things nice. Yeah, so we're almost done with the background here, I promise. So an algebra might have a dual if its binary operations and distinguished elements are swapped. So the same arbitrary sequence can be expressed in both, in a particular sentence is dualized or pushed into some negative space. So I can point to the intuition between, say, a row space and a column space of a vector space. Um, and each operation has its dual. So the inner cylindrification is defined by the represented formula corresponding to the for all quantification. So if anyone's read like first order sentential logic before, you will see that the negation of the existential operator and the negation of the variable leads us to the for all operator, and we just have some like special notation for that here. So we can also generalize each operation with a set delta, which contains a set of variables, which causes us to cylindrify or diagonalize over all the variables in that set at the same time. So we need some special notation for the generalized complement of the diagonal, which is called the generalized co-diagonal operator. So we now have some illustrative results to tell you why cylindric algebras are interesting. So we first move into the similarity theorem. So the free algebra of formulas is similar in the sense of similarity types to the corresponding cylindric algebra of some arbitrary cardinal alpha, which is less than that of the natural numbers. We also note that the cylindric algebras of formulas for some language belongs to the cylindric algebra of also belongs to that cylindric algebra. And these equivalence classes are important to study for reasons that I've mentioned before. So they're a smaller subclass that denotes some truth structure, which tells us something about the larger class. Um, Okay, so we have some basic substructure here. So it turns out that the cylindric algebra formulas for some language is equivalent to the cylindric algebra formulas for some theory of that language, because the theory is precisely the set of logical consequences for each model of that language. And if a cylindric algebra can be represented as being the direct product of certain algebras, and those algebras also happen to be cylindric algebras, we now have some smaller truth structure that can tell us something about a larger one. And this is called the representation problem of cylindric algebras, and that's a set of that's a whole subject of study in the second volume of the Tarski book that I've referenced. And this is, I think, the main theorem that gives you an intuitive sense as to what's going on. So the notation we have constructed carefully before this lets us understand this theorem, but you don't directly have to interpret what's going on. It does entail the logical equivalence of both the sentences that you see down below. And intuitively, it seems clear that both these sentences are equivalent to each other. But it's clear to anyone who's seen proofs in elementary logic before that this is non-trivial to prove. But you'll have to take my word for this. The proof of theorem 20 that you see here is like 5 or 6 lines. So what cylindric algebras does for us through its construction is it affords a really large economy of proof, I should say. In terms of the fact that the proof actually has a lot of intuitive content that we can interpret. So finally, we go through an exposition of Robbin's problem. So Alfred Tarski was in fact very taken by this problem for a while and went around posing it to his friends and collaborators, explaining why it's placed in his book, Cylindric Algebras. And we care about it because if we are able to apply cylindric algebras to one problem of axiomatizability, then the methods developed would be used for similar problems. So again, we go through some slight background here. So what's represented here is a very formal definition, but the quick version of it is this: a polynomial algebra represents all possible variations of polynomials constructed using the treatment of variables as axes. And we have a few examples given below, but we've restricted ourselves to the two variable case because that's just simpler. So we now define what a polynomial is in that polynomial algebra. So as intuition suggests, the first definition formalizes the fact that we can have both variables and constants within the set of classes of polynomials. And equivalence classes of polynomials are defined in the natural way. And they are definitionally equivalent if we are using the same sentences that generate the equivalence class of other true or false sentences. So we now have a preliminary result that we use in Robbin's problem just after this. So this the set inclusion of point two, I mean here, is a consequence of point number one, and we basically need to show that the fundamental operation of one algebra can be shown as a polynomial over the other, and that entails the set inclusion that we see in point two. Okay, so I'll read out Robbin's problem for the sake of completeness. So Boolean algebras can be treated as algebraic structures, and so you'll notice that this tuple doesn't have the product operation with the usual meaning and or. Clearly, the class of Boolean algebras so treated is definitionally and in fact polynomially equivalent with the class of Boolean algebras described as another tuple, but in this case, you'll notice that it has the product operation. And we're just redefining the axioms of Boolean algebra here. So we have basically commutativity and idempotence and associativity. Um, and here's the statement of Robbin's problem itself. So is it that Boolean algebras under the new construction can be characterized as algebras in the newer sense? So these have to satisfy the following postulates. So we have again associativity and commutativity, and the third condition is what's known as Robbin's equation. So the previous axiom set actually contained the equation that we have down below, which is Huntington's equation. And Herbert Robbins posed the question of whether we can reduce Huntington's equation to Robbins equation, which is R3 here, and whether that is a complete axiom set for Boolean algebras. And so if you just look at the two equations, it might just seem like it's algebraic manipulations to get to Robbins equation. But in fact, it's not as simple as that. But it turns out there is a non-trivial proof for that, which was found by William McCune in 1997. And he used an automated theorem solver to do that. And the solver's proof, even with redundancies, had over 8,000 lines in that elementary proof. And of course, you can imagine that an 8,000 line proof with just elementary steps doesn't give you a lot of intuitive content. So we can go some ways in terms of defining what's going on. So So we notice that we need to remove the product operation. So we can in fact prove that in the Boolean algebra in the newer sense and the older sense are polynomially equivalent. So we recall the fact that Boolean algebras in fact are they encode the De Morgan laws, which allows us to redefine the fundamental operation of the sum in terms of the product, which you see below. And using the preliminary result of the set inclusion, we can in fact prove that the two Boolean algebras are definitionally and polynomially equivalent. And okay, we can go a little further in the sense that we can define or like re-express R1, R2, and R3 in terms of cylindric algebras. So what we do here is we universally quantify over all variables, and you'll notice that the quantification didn't exist in the original statement. And the proof of why we can do this is there in Paul Cohen's book, but I mean, it's kind of intuitive to see why. So again, we're able to express this in cylindric algebras, but just because we can express it doesn't mean that we can use cylindric algebras yet to prove its axiomatizability. So that's still an open problem of whether we can use cylindric algebras as a useful method to prove this problem. And yeah, so hopefully I've convinced you that cylindric algebras are a useful method for doing predicate logic. And yeah, that's it for me. I will leave the references on for a second so that you all can see it.
Thank you very much, Sarbajit, for the very informative presentation. I thoroughly enjoyed that. I haven't studied algebra in a very long time, so it was nice seeing it again. So now's the time. We've got about 3 minutes for questions. So people in the room, you're either welcome to pop your hand up on Zoom or write it in the chat and I can read it out for you. But it really is truly astonishing that there is a way you can take a proof that is, almost 9,000 lines. And I
Mhm.
assume that's 9,000 lines in the code, right? Rather than like 9,000 written lines. But to go from that to what it seems to be a few statements using cylindric algebra is quite impressive.
Yeah, yeah. I agree. I mean, I really think it's very beautiful. I mean, I feel like beautiful is a word that's overused with mathematics, but this really popped out to me.
Yeah, I mean, it's immense,
Yeah.
really. So do you think that the cylindric algebras will be able to do this to any other problems? Are there any, or maybe the question should be, are there any other problems that you think might be well suited for cylindric algebra?
Um, so in terms of problems in axiomatizability, I think I mean that's above my pay grade to answer. Like I don't know. Although I have seen it being used in proving some theorems in so most of the time cylindric algebras are in fact used for economy of proof. So I can't remember exactly, but there was this theorem that Tarski and his other authors proved in the second volume of their book, which was in Lie groups. And the proof within, like, say, we'll call it an elementary Lie group proof, which means that we've defined what a Lie group is, and then we're trying to prove something from that. They in fact translated that into cylindric algebras, and they were able to prove that same statement much quicker. So I think that has been used before, but I haven't seen a lot of uses in axiomatizability. Personally, like I haven't seen it.
So do you think that this idea can be used to improve computer-based proofs?
Yes, that is something I'm optimistic on because again, this is a symbolic language, right? And
Yeah.
it can easily be translated, and I feel like there is a lot of good work that can be done in this case.
Mm. Nice.